Welcome back, Design Junkies, to Mechanical Engineering Made Simple. If you enjoy the podcast, show your support with a like, a follow, or a comment.
Yeah, it's really great to be back for another one.
So usually when we think about engineering, or I don't know, even something like a medical diagnosis, there is this expectation of like absolute visible precision.
Right, people want certainty.
Exactly. You know, you break your arm, they put you in an x-ray machine, the film comes back showing that jagged white line, and the doctor just points at it and says, there it is.
Yeah.
It's incredibly comforting, you know?
It is. It's binary, it's broken or not broken. We inherently like things to be visible, discrete, and easily categorized.
Totally.
I mean, in solid mechanics, you have a steel I-beam, you have a concrete pillar, you can walk right up to it, hit it with a hammer, measure its exact length with a tape measure.
Right.
And then you calculate exactly how much weight it can hold before it snaps.
But what happens when the materials you are building with or, designing for don't stay put?
That's the big question.
Right. Like what happens when you step into a world where that X-ray machine of certainty is just completely broken and the physical landscape is constantly flowing and deforming and swirling and shifting right beneath your feet?
It's a completely different ballgame.
It really is. So today our mission in this deep dive is to uncover the hidden underlying rules of the most chaotic substances on Earth. We are diving into the invisible world of fluid mechanics.
And it is a wild world once you really get into it.
Oh, absolutely. We're going to look at how the exact same invisible forces and mathematical laws govern everything from a single microscopic dewdrop resting perfectly still on a taro leaf, all the way up to the chaotic, immense, terrifying swirl of a Category 5 hurricane.
Which requires a massive shift in perspective for any engineer or designer.
For sure.
Fluids, and keep in mind, this encompasses both liquids and gases. They demand a completely different conceptual language than solids. You can't just measure a block of water and expect it to stay a block.
Exactly. So today, we are going to translate these heavy, often intimidating concepts into mind-blowing aha moments.
I love those moments.
Me too. By the time we wrap up, you are going to completely change how you look at a simple glass of water sitting on your desk or the weather fronts forming outside your window.
Or even the aerodynamic curves carved into the bodywork of your car.
Yes. So I think the most logical place to start this journey is at the absolute foundation.
Makes sense. Where are we starting?
Before we can even begin to understand how massive bodies of water like oceans or vast weather systems move and interact, we first need to define what exactly makes a fluid a fluid.
Right. And perhaps more importantly, why water and air, which are both technically fluids, behave so incredibly differently when you put them under pressure.
Yeah, because if I call air a fluid, a lot of people might, tilt their head. We instinctively think of fluid as liquid.
Sure, that's the common everyday definition.
But the scientific definition divides fluids into two distinct categories, liquids and gases. And there is a fundamental difference in how they occupy space.
There is.
There's that ancient saying, water takes the shape of the vessel containing it. But a liquid also has a very specific boundary. It has what engineers call a free surface.
Right, the free surface is key.
If you pour water into a coffee mug, it takes the shape of the bottom and the sides of the mug, but it stops at a certain height. It creates a flat top.
Yes.
It doesn't magically expand upward and outward to fill your entire kitchen.
Precisely. That upper boundary, that flat top resting under the air, is the free surface. It is a defining characteristic of a liquid.
Okay, so what about gases?
Gases, conversely, do not possess a free surface. A gas is highly compressible and possesses an inherent kinetic energy that causes it to expand indefinitely.
So it just keeps going.
Exactly. It will completely fill whatever container you put it in, no matter the size.
Wow.
If you release a small pressurized tank of helium inside a completely sealed room, that helium doesn't just pool on the floor like spilled water.
Right, it doesn't just sit there.
No, it disperses, diffuses, and spreads until it occupies every single cubic centimeter of the available space in that room.
So their relationship with space and volume is a massive dividing line. Liquids hold their volume, gases expand their volume.
That's a good way to put it.
Liquids are incredibly hard to compress. Gases are famously easy to compress. But there is another characteristic that defines a fluid, and this is where the physics get really interesting: viscosity.
Ah, yes. Viscosity is the absolute key to understanding fluid behavior.
Let's break that down.
Think about a solid block of rubber. A solid shows its elasticity when you subject it to tension by pulling it, or compression by squeezing it, or shear stress by twisting it.
It fights back.
Exactly. It fights back against all those forces. But a fluid is different. A fluid really only pushes back against compression.
Okay.
It offers zero resistance to being deformed or stretched. However, a fluid does show a very specific type of resistance when two internal layers of it try to slide over each other.
So that's internal friction.
Exactly. That resistance to sliding layers is what we call viscosity.
I want to make sure we visualize this properly. Imagine a brand new deck of playing cards sitting on a table.
Okay, I'm picturing it.
If I put my hand flat on the top card and slide my hand forward, the top card moves with my hand.
Right.
But the friction between the cards means the second card slides forward just a little bit less, and the third card even less, all the way down to the bottom card, which is stuck to the table and doesn't move at all.
Yes.
You get this slanted, staggered profile of cards.
That is a brilliant way to visualize it. In fluid mechanics, Isaac Newton actually gave us the mathematical definition for this exact sliding behavior.
Good old Newton.
Always showing up, right? Instead of sliding cards, imagine sliding layers of water. Newton's law of viscosity explains the relationship between the force you are applying to slide the fluid and how the fluid reacts.
Okay.
Now, without getting bogged down and reading raw calculus variables, the core concept is a relationship between shear stress and the velocity gradient.
Let's break those terms down so they physically make sense to you listening.
Shear stress is simply the force per unit area that is trying to slide the fluid layers.
So it's my hand pushing on the top card.
Yes. And the velocity gradient is a measure of how the speed of the fluid changes as you move further away from the boundary, like the wall of a pipe or the table under your deck of cards.
Okay, got it.
The fluid right against the wall is essentially stationary, but the fluid perfectly in the middle of the pipe is moving the fastest. The change in speed between those 2 points is the gradient.
And the connection between that pushing force and that speed change is the dynamic viscosity, essentially, the thickness or the stickiness of the fluid.
Precisely. And the math actually looks like this. Tau equals mu times the derivative of up with respect to y.
Where tau is the shear stress, right?
Right, and mu is the dynamic viscosity.
Okay, so if a fluid obeys this law perfectly linearly, meaning if you push twice as hard, the fluid slides exactly twice as fast, it is called a Newtonian fluid.
Which is the ideal scenario for us engineers.
Water is our classic Newtonian fluid. Air is also a Newtonian fluid, but nature isn't always that clean, is it?
Definitely not.
There are rebel fluids out there that refuse to follow Newton's rules.
Yes, the non-Newtonian fluids. They are endlessly fascinating and, honestly, notoriously difficult to engineer around.
Why is that?
Because non-Newtonian fluids do not have a constant viscosity. Their thickness actually changes depending on how much shear stress you apply or how long you apply it.
The classic science fair example is oobleck, right? That mixture of cornstarch and water.
Exactly. Oobleck is a perfect example.
If you gently push your hand into a bowl of oobleck, it slides in like a thick liquid.
Right.
But if you punch it with your fist, the sudden application of intense shear stress causes the particles to lock together, and it suddenly acts almost like a solid brick. You bounce right off.
Yes, that is a shear thickening fluid. But there are also shear thinning fluids, where applying force actually makes them runnier. Think of ketchup. You have to smack the bottom of the glass bottle to introduce shear stress, which thins the ketchup enough for it to flow out.
Oh, wow. I never thought of ketchup like that.
Yeah, it's a non-Newtonian fluid. And on an industrial scale, engineers deal with non-Newtonian fluids constantly.
Like in what industries?
Liquid asphalt, wet concrete, drilling muds in the oil industry, certain high molecular weight, polymer solutions, even human blood under certain conditions.
Really? Blood.
Yep. The entire scientific field of rheology is dedicated solely to studying these complex deformations.
It's amazing how complex everyday substances can be. But even if we go back to our standard predictable Newtonian fluids like pure water and air, there is a completely counterintuitive effect when you introduce temperature changes.
This is one of my favorite quirks in physics.
I always grew up thinking that heat just generally melts things, it makes things runnier. But in fluid mechanics, that rule entirely depends on whether you are dealing with a liquid or a gas.
Exactly.
If you heat a liquid, its viscosity decreases, it gets thinner and runnier.
Right. From a molecular standpoint, heating a liquid adds energy. The molecules become more active and spread slightly further apart.
Okay.
This increased distance drops their mutual attraction to one another so they can slide past each other much more easily.
Think of heating up a jar of cold, thick maple syrup. It goes from a slow, gooey crawl to pouring almost like water.
That's a great example.
Yeah.
But if you heat a gas, the exact opposite happens.
And this blows my mind. The viscosity of a gas actually increases as the temperature rises. Heat makes a gas thicker and harder to slide through.
It seems like a paradox, doesn't it?
It really does.
But if you think about the kinetic theory of gases, it makes perfect sense. In a gas, the molecules are already very far apart.
Right.
The internal friction, the viscosity, isn't caused by the molecules holding hands and resisting being pulled apart, like in a liquid.
So what causes it?
In a gas, viscosity is caused by the molecules colliding with each other as they zip around.
I love the analogy for this. Imagine a crowded room full of people at a networking event. If the room is cool and quiet, everyone is relaxed, maybe slowly strolling around or standing still. If you need to walk from one side of the room to the other, you can easily weave your way through the crowd, slipping past people without much resistance.
Right.
That is a low temperature, low viscosity gas.
But then, imagine you crank the heat up,
Yeah.
pump high-energy dance music into the room, and suddenly everyone in the room starts sprinting frantically in completely random directions.
That's overall chaos.
Exactly. They're bouncing off the walls, colliding with each other, crossing paths chaotically. If you try to walk from one side of the room to the other now, it becomes incredibly difficult.
Because you're just bumping into everyone.
Yes, people are constantly slamming into you, impeding your forward progress. You're experiencing massive resistance. That chaotic, vigorous molecular movement increases the mixing and the internal friction.
So high temperature equals high viscosity in a gas.
Precisely.
That visualization just makes the invisible world so clear, and it highlights something fundamental about the challenges engineers face.
It really does.
A fluid is, in reality, just an aggregate of billions and trillions of individual molecules, all bouncing around like those people in the room.
True.
But trying to keep track of every single molecular collision in a pipe or over a car hood is mathematically impossible, even for supercomputers.
It's way too much data. So engineers rely on a foundational assumption. They treat a fluid as a continuous isotropic substance.
Which means what? Exactly. Because to me, it sounds like they are just pretending the fluid is a perfectly smooth, uniform block of jelly rather than a microscopic ball pit full of individual plastic spheres.
Honestly, that is exactly what they are doing.
Okay, good to...
It's a macroscopic approximation. And they can get away with this mathematical shortcut because the scale we exist on is so vast compared to the molecules.
How vast?
Well, consider the mean free path of air. This is the average distance a single molecule of air travels before it violently collides with another molecule.
Okay.
At normal room temperature and atmospheric pressure, that mean free path is roughly 0.006 micrometers.
That is unimaginably tiny. So tiny that we can't even process it.
Exactly. So at any macro scale that a mechanical engineer actually cares about, whether they are sizing a copper water pipe for a house or designing the massive swept wing of a commercial airliner,
Right.
treating the fluid as a perfectly continuous medium with no microscopic gaps works perfectly. The individual molecular chaos averages out into smooth, predictable bulk properties.
So what does this all mean for you listening? It means that the next time you look at a pot of boiling water or feel a hot summer breeze hit your face, you'll never experience it the same way.
No, you won't.
You're actually feeling that heat fundamentally altering the internal kinetic thickness and the friction of the invisible fluids surrounding you.
It really is a beautiful system.
Yeah.
But moving on from the internal sliding and friction of fluids, we have to look outward.
Out to the edges.
All right. We have to ask, what happens at the very edges? What happens at the boundary where a body of liquid meets the air or where it comes into contact with a solid wall?
This brings us to a fascinating topic. The hidden architecture of liquids. The secret forces of tension and compression that act at the boundaries.
Let's start with surface tension.
Yeah, if you zoom in on the surface of a liquid, it behaves exactly like a stretched sheet of rubber that is constantly trying to shrink.
It really does.
This is why, if you step outside in the early morning and look at a dewdrop resting on a leaf, it forms a nearly perfect little sphere.
It's a marvel of molecular physics.
Yeah.
Inside the main body of the water drop, every water molecule is surrounded by other water molecules on all sides.
Okay.
They're being pulled equally in every direction by cohesive forces, specifically hydrogen bonds. So they are balanced.
Right, they're perfectly comfortable.
But the molecules right at the surface don't have water above them. They only have air. So they are pulled strongly inward by the water below them and sideways by their neighbors, but not upward.
So they're getting yanked down.
Exactly. This creates an unbalanced inward tug, a microscopic tension. The liquid is literally pulling itself inward, trying to minimize its surface area as much as physically possible.
And geometrically, the shape with the smallest surface area for a given volume is a perfect sphere.
Precisely.
What's wild to me is how this tiny microscopic surface tension dictates the massive internal pressure of that dewdrop, or the pressure inside a bubble floating in your soda.
The internal pressure of a spherical droplet is governed by a very precise balance of forces.
And what's the math on that?
The mathematical relationship states that delta P equals 4 times T divided by D.
Okay, let's unpack that.
It means that the increase in internal pressure delta P is directly proportional to the surface tension, T, but inversely proportional to the diameter of the drop, D.
Let's focus on that last part because it's crucial. The diameter of the drop is the dividing factor.
Yes.
This means as the bubble or the droplet gets smaller and smaller, the internal pressure skyrockets. A large soap bubble has very little internal pressure. It's fragile and floppy. But a microscopic bubble, one you can barely see with the naked eye, it has an exponentially higher internal pressure.
Because the curvature is so tight, the elastic film of the surface tension is wrapped so sharply around that tiny volume that it is squeezing the interior fluid with immense, almost crushing force.
Wow.
But surface tension doesn't act in a vacuum. It frequently battles with other forces, specifically adhesive forces, when the fluid touches a solid surface.
And this battle gives us one of my favorite physical phenomena: capillarity.
Capillarity is a perfect example of forces competing in plain sight. It is the interaction between cohesion, the fluid's love for itself, and adhesion, the fluid's love for a different material.
So if you take a very fine, thin glass tube, open at both ends, and place it straight down into a cup of water, the water doesn't just sit there.
No, it doesn't.
It actually climbs up the inside of the glass tube, entirely defying gravity.
Exactly. And that's because the adhesive force between the water molecules and the molecules of the glass wall is stronger than the water's own cohesive surface tension.
So the water essentially wants to stick to the glass more than it wants to stick to itself.
Yes. So it reaches up, grabs the glass, and pulls itself upward until the weight of the water column finally balances out the pulling force.
But here's where it gets really interesting. If you take that exact same glass tube, wipe it clean, and place it into a pool of liquid mercury, the exact opposite phenomenon occurs.
Mercury is fascinating.
The mercury doesn't climb. It is actually pushed down inside the tube, ending up lower than the surrounding pool.
Right.
And the surface of the mercury inside the tube forms a convex meniscus. It domes upward in the middle, curving away from the glass walls.
It's like the mercury is actively repelled by the glass.
In a sense, it is. This occurs because the cohesive force of the mercury atoms holding onto each other is massively stronger than any adhesive attraction they might have to the glass.
The contact angle of mercury to a glass wall is incredibly steep, between 130 and 150 degrees.
So it wants nothing to do with the glass.
Nothing at it. So it pulls inward on itself, depressing the level inside the narrow tube.
So we've got fluids stretching like rubber, sticking to walls and repelling materials. But what about squeezing?
Compression.
Earlier, we said a defining trait of liquids is that they are incredibly hard to compress. And honestly, almost every engineering textbook will plainly state that water is an incompressible fluid.
They will say that, yes.
But wait, stop right there. I know that in reality, engineers constantly use simplified models like the perfect fluid or the ideal gas.
Sure.
These are models that don't actually exist in the physical universe. They are just used to make the math workable on a chalkboard. Are you telling me that calling water incompressible is just one of those convenient lies?
You are absolutely right to call that out. Calling water purely incompressible is absolutely an engineering approximation. It is a very useful, very convenient lie.
I knew it!
In the physical reality of our universe, under extreme pressure, water absolutely does yield its squishes.
Okay, so it has a limit.
Right. It has what physicists call a bulk modulus, which is a measure of a substance's resistance to uniform compression. However, it takes a truly massive amount of force to see it.
How massive?
If you take a volume of water at a normal room temperature and you increase the surrounding pressure by a full standard atmosphere, which is roughly 14.7 pounds of force per square inch, the entire weight of the sky pressing down on us.
Right, 1 atmosphere.
The water's volume only shrinks by about 0.0005%.
That is a tiny microscopic fraction.
Almost negligible.
So if you are designing a municipal plumbing system or the water lines for a new house, assuming the water doesn't compress makes your math infinitely easier.
Oh, massively easy.
And that 0.005% variance is never going to burst a pipe or ruin your final design.
Exactly.
But it makes me wonder, if water really is slightly compressible, does that tiny fraction ever actually matter in the real world? Or is it just a trivia fact for physicists?
Oh, it matters immensely. It is fundamentally responsible for life and communication in the oceans.
Wait, really?
Yes. If water were perfectly purely incompressible, exactly as the simplified engineering models suggest, the entire field underwater acoustics simply wouldn't exist.
How does compressibility relate to sound?
Think about what a sound wave actually is. Sound is not a physical object. It is a mechanical pressure wave propagating through a medium.
Right, like ripples in a pond.
Exactly. It requires the molecules of that medium to bump into each other, compress together slightly, and then spring apart, passing the energy down the line.
Oh, I see where this is going.
The speed of sound in any fluid relies entirely on this slight compressibility.
What's the formula for that?
The physical relationship dictates that velocity equals the square root of k divided by rho.
Okay, let's translate that.
Velocity is the speed of sound. K is the fluid's bulk modulus, its resistance to compression. And rho is its density.
Let me wrap my head around that. The bulk modulus is the resistance to compression. So if a perfect fluid is purely incompressible, its bulk modulus would technically be infinite.
Yes, theoretically.
Which means, according to that math, the speed of sound in that perfect incompressible fluid would also be infinite.
Right.
The sound wave would travel instantly from one side of the ocean to the other, which completely breaks the laws of physics.
It would violate relativity, yes.
So without that tiny 0.0005% yield, a submarine sonar system wouldn't function. Whale songs couldn't travel for hundreds of miles.
Because the pressure waves wouldn't have any squish to travel through.
The entire ocean would be completely deaf and silent.
Exactly. The gap between pure, simplified math and complex physical reality is where all the most beautiful and interesting phenomena live.
That's incredible.
That microscopic, almost negligible, slight squishiness of water is the only reason marine mammals can communicate over vast distances in the dark.
That is such a great aha moment. Okay, so we've looked at the microscopic scale, the tiny dewdrops, the climbing capillary tubes, the microscopic compression of sound waves. Let's scale up. Let's look at millions of gallons of water. This brings us to fluid statics, the crushing, massive reality of still water. What happens when we take massive amounts of fluid and stack it up against a wall, like a hydroelectric dam?
To understand the sheer power of fluid statics, we first have to go back to the 17th century and understand Pascal's law.
Blaise Pascal, right?
Yes, Pascal was a brilliant French mathematician and physicist. He realized a fundamental truth about confined fluids. If you apply pressure to a fluid that is totally enclosed in a vessel, that pressure is transmitted equally and undiminished to every single part of the fluid, into the walls of the vessel.
Meaning the fluid doesn't absorb the pressure in one spot, it instantly shares it everywhere.
Exactly.
This is the absolute magic behind the hydraulic press. Let's visualize a closed system with two pistons, essentially two plungers pushing into a sealed fluid reservoir.
Oh.
One plunger is very small, maybe an inch across. The other plunger is massive, maybe a few feet across.
Right. Now, pressure is defined as force divided by area. So if you push down on the small plunger with a small amount of force, say 10 pounds, you create a specific amount of pressure in the fluid because that small force is concentrated on a small area.
But because of Pascal's law, that exact same pressure is instantly transmitted through the fluid to the large plunger.
Yes. And the math for this is F2 equals F1 multiplied by A2 divided by A1.
So force 2 equals force 1 times the ratio of their areas.
Exactly. And since pressure equals force divided by area, if the area of the second plunger is massive, the resulting outward force must also be massive to keep the equation balanced.
The force is amplified exponentially based on the ratio of the areas. You can literally lift a 2-ton car off the ground by simply pushing down on a small lever with your bare arm.
It feels like you are cheating the universe, creating energy out of nowhere.
It really does.
But you aren't. It's simply the beautiful geometry of fluid statics. You have to push the small plunger down a very long distance to move the big plunger up just a tiny bit so the work balances out.
That's in a closed, artificially pressurized, man-made system. But in the natural world, like a deep lake or the Mariana Trench, pressure isn't created by a plunger.
No, it's not.
It's created purely by gravity pulling down on the immense weight of the fluid itself. And in a liquid, pressure increases linearly with depth.
Yes. The formula is P equals P0 plus rho times G times H.
So P is the total pressure. P0 is the atmospheric pressure pushing down on the surface of the lake.
Right.
And then you add rho, the density of the liquid, multiplied by G, gravity, multiplied by H, which is your depth.
Because water's density is incredibly constant, remember, that tiny 0.005% compressibility doesn't really change its density much. The pressure goes up in a perfectly straight, linear line as you dive deeper.
So for every 33 feet you go down in the ocean, the pressure increases by 1 full atmosphere. It is relentless, predictable, and crushing.
But gases, again, play by different rules.
Of course they do.
We live at the very bottom of an ocean of air. Atmospheric pressure changes as you climb a mountain, but it does not change linearly because air is highly compressible.
Its density thins out dramatically with altitude.
Exactly. The lower layer of Earth's atmosphere, the troposphere, is a great example. As you climb up through the troposphere, the temperature drops about 0.65 degrees Celsius for every 100 meters you ascend.
But it doesn't keep dropping forever.
No, it eventually hits a boundary. Around 10 to 11 kilometers up, the temperature caps out at a brutally constant negative 50.5 degrees Celsius.
Which, not coincidentally, is precisely the altitude that commercial airliners choose to fly at.
Right.
They cruise in that extremely cold, incredibly thin, low-density air, where the pressure is a fraction of what it is down at sea level. That thin air dramatically reduces the friction and aerodynamic drag on the aircraft, saving thousands of gallons of jet fuel.
So knowing how crucial pressure is, how do engineers actually measure it? You can't just look at water and know its pressure.
Obviously not.
The field has developed several incredibly clever, purely mechanical devices. Historically, the most reliable are manometers.
Manometers.
Yes. These use literal columns of liquid to balance and measure the invisible pressure.
Let's explain the U-tube manometer. It is exactly what it sounds like. A glass tube bent into the shape of a U.
Okay.
You fill the bottom of the U with a dense liquid, like mercury. You connect one top end of the tube to the pressurized pipe you want to measure, and you leave the other top end open to the room air.
Right.
The pressure from the pipe pushes down on the mercury on its side, forcing the mercury on the open side to rise up.
Yes.
You literally just hold a ruler up to the glass tube and measure the height difference between the two columns of mercury. That height difference tells you the exact pressure. It is beautifully simple.
But what if you were trying to measure minute fluctuations in pressure? A change so small, the mercury might only move a millimeter.
It's too hard to read accurately.
Exactly. So engineers developed the inclined manometer. Instead of a vertical U, they take the measuring glass tube and tilt it at a very shallow angle, almost horizontal.
Okay, I see.
Because of the tilt, a tiny vertical change in pressure forces the liquid to travel a very long horizontal distance along the glass tube just to gain that millimeter of height.
Oh, that's clever.
It physically magnifies the reading across a long scale, so it can be easily and accurately read by the human eye.
It's stretching out the data physically. I love that.
Yeah.
And then there's my absolute favorite pressure gauge, the Borden tube.
Ah, a classic.
I love the mechanical elegance of this device. It was invented by Eugene Borden in the 1800s. If you walk into any industrial plant or look at an air compressor in a garage, you'll see these analog pressure gauges with the little needle on a dial.
Right.
Inside that gauge is a Borden tube. Let's walk through how it works because it relies on a brilliant geometric trick.
Okay, lay it out.
Inside the gauge is a curved metallic tube. It's bent into a C shape. But the secret is that the tube doesn't have a perfectly round cross-section like a garden hose. It has an elliptical, flattened cross-section.
Yes.
One end of this C-shaped tube is fixed in place and connected to the pressurized fluid. The other end is sealed shut and free to move.
So when pressurized fluid enters that hollow tube, Pascal's law tells us the pressure pushes outward equally in all directions against the interior walls.
Right.
Because the tube is flattened into an ellipse, the pressure tries to force the walls outward to maximize the internal volume. It tries to force the flattened ellipse to become a perfect inflated circle.
And here's the genius part. As the cross-section tries to bulge from an ellipse into a circle, it forces the entire C-shaped curve of the tube to straighten out slightly.
It uncurls.
Exactly. It uncurls just like a paper party blowout toy when you blow into it.
That's a great visual.
That tiny physical uncurling motion at the free end is attached to a tiny gear. As it uncurls, it turns the gear, which spins the needle on the dial. The higher the pressure, the more it tries to become a circle, the more it uncurls, and the higher the needle points.
It translates invisible fluid pressure into purely mechanical rotational motion.
It is brilliant. And if we pull back and connect this deep understanding of pressures to the bigger picture, mastering these calculations is exactly what allows us to build monumental, landscape-altering structures safely.
Like dams.
Consider the terrifying engineering problem of designing a massive hydroelectric dam or the steel sluice gates that hold the water back. You are dealing with a wall of water where the pressure is zero right at the very surface, but it becomes absolutely crushing at the bottom of the dam.
Right, and this leads to a great riddle for you listening at home. I want you to visualize this.
Let's hear it.
Imagine you are the engineer designing a large rectangular steel underwater door, a sluice gate, built right into the flat vertical face of a dam. The water pressure is pushing massively against it. You need to put a hinge and a robotic arm on the back of this door to hold it shut. So you need to find the absolute center of that pressure.
The point of balance.
Right. Where is the single point on that door where all that varying force effectively balances out?
Naturally, human intuition screams, it's a rectangle, it's symmetrical, so the center of pressure must be dead center, right in the geometric middle.
But if you build the hinge in the geometric middle, the door will fail catastrophically.
Why?
Because the center of pressure is always lower than the physical geometric center.
Because of the depth.
Exactly. Remember, pressure in a liquid increases linearly with depth. That means the water pushing against the bottom half of your rectangular door is significantly deeper than the water pushing against the top half.
Therefore, the bottom half is experiencing significantly more force. It's a lopsided load.
The aggregate force is physically shifted downward.
Exactly. To find the exact location of that shifted point, engineers have to use a concept called the geometrical moment of inertia.
Which is tricky math.
Finding the total overall force on the wall is relatively easy. It's just the pressure at the geometric center multiplied by the total area. But to find where that force actually acts the exact coordinate where you must attach your hinge so the door doesn't twist, you have to calculate the moment of inertia for the shape of the gate.
Right, which involves integrating the increasing pressure over every square inch of the area.
And that math proves that the action point is shifted below the center. If engineers blindly trusted their intuition and didn't account for this downward shift, the unbalanced torque from the deeper water would literally rip the hinges right off the steel gate.
It is a perfect, sobering example of how our human intuition fails us, but the rigorous math of fluid mechanics saves the day and keeps the dam intact.
So we've spent a lot of time looking at how static water crushes inward and pushes sideways against walls, but we have to flip that around.
What do you mean?
How does that exact same pressure network suddenly create an upward lifting force? How does water hold things up? And what happens when a still body of water interacts with a moving object or is suddenly violently accelerated?
To answer that, we have to go back to ancient Greece, around 287 BC, and look at the genius of Archimedes.
Archimedes!
He wasn't just an abstract philosopher, he was a very practical engineer. He invented the Archimedes screw, a massive rotating spiral used for pumping water out of the hulls of sinking ships, and he studied centers of gravity extensively.
But his most famous and lasting legacy in fluid mechanics is, of course, Archimedes' principle.
We all know the legend of him shouting "Eureka" in the bathtub, realizing that his body displaced an exact volume of water.
Right.
But the principle he derived from that is foundational. It states that the upward buoyancy force exerted on any body completely or partially immersed in a fluid is exactly equal to the weight of the fluid that the body displaces.
Let's trace the logic of that. If you take a solid, heavy block of raw steel and drop it into a pool, it sinks straight to the bottom.
Right, obviously.
Why? The steel block displaces a certain volume of water, a volume exactly equal to its own size. The Archimedes' upward buoyancy force pushing back on the steel is equal to the weight of that specific cube of displaced water.
But because steel is physically much denser than water, that small cube of displaced water weighs far less than the heavy steel block.
Gravity wins, the downward force is greater, and the block sinks.
But if you take that exact same weight of steel, melt it down, and forge it into the shape of a large hollow boat hull, you change everything.
You're spreading the weight out.
Exactly. When you place the boat in the water, it displaces a massive volume of water because of its wide, hollow shape. The weight of all that displaced water is immense, generating a massive upward buoyancy force that easily counteracts the downward weight of the steel.
The downward pull of gravity and the upward push of buoyancy perfectly cancel each other out, and the ship floats.
It's an elegant balance. But making a ship float is honestly only half the battle for a marine engineer.
What's the other half?
The much harder half is making sure the ship stays upright when the ocean gets rough. Ship stability is a constant, delicate, and mathematically complex dance between two invisible points: the center of gravity, which we'll call G, and the center of buoyancy, which we'll call C.
Okay, let's unpack this invisible dance. The center of gravity, G, is the balance point of the ship's actual mass. All the steel, the engines, the cargo, the crew.
Right.
Unless you are actively moving heavy cargo around on the deck, point G is relatively fixed in space relative to the ship.
Yes.
But the center of buoyancy, C, is the center of the displaced water's volume under the hull. And here's the trick that messes with people's heads. As a ship rolls to the side in a wave, leaning heavily to starboard, the actual physical shape of the underwater portion of the hull changes.
Because the water level shifts relative to the boat.
Exactly. One side dips deeper, the other side lifts out of the water. Because the underwater volume changes shape, the center of buoyancy, C, physically moves out to the side.
It shifts laterally to the side the ship is leaning. And this lateral movement is what dictates survival or disaster. You now have the downward pull of gravity acting straight down from G, and the upward push of buoyancy acting straight up from the new shifted C. Because they are no longer perfectly lined up vertically, these two forces create a rotational couple, the torque.
And to figure out which way that torque is going to twist the ship, engineers find a third magical point.
The metacenter.
Right. They draw a vertical line straight up from the new shifted buoyancy center. The exact point where that upward line intersects the ship's original vertical center line is called metacenter, or M.
The location of the metacenter is everything. It is the ultimate arbiter of stability.
How so?
If the metacenter, M, is located high up above the center of gravity, G, the ship is considered stable. The rotational torque created by the forces will act as a righting moment. It will forcefully twist the ship back to an upright, level position.
But if you mess up the design or load too much heavy cargo on the top deck, raising the center of gravity,
then you have a problem.
Yeah, if M ever falls below G, it is a catastrophic disaster. The forces align in the opposite direction, creating an overturning moment. The ship's own buoyancy works against it, pushing the ship further over until it completely capsizes.
Exactly. And naval architects meticulously manipulate the distance between G and M, known as the metacentric height, depending on what the ship is designed to do.
So they customize it?
They do. They don't just want a stable ship, they want the right kind of stability.
Right.
For a military warship, like a destroyer, you need an incredibly stable, rigid platform for firing weapons accurately.
Right.
So you design the hull with a very large metacentric height, generally 0.8 to 1.2 meters.
Which means if a massive rogue wave hits the side of a warship and rolls it over, the righting force is immense, and the ship snaps back to an upright position very aggressively and violently.
It's safe, but it's a brutal ride.
Extremely brutal, but you absolutely do not want that on a luxury cruise ship.
Definitely not.
If a massive 15-story passenger ship snapped back violently every time a wave hit it, plates would fly off tables, people would be thrown into walls, and everyone on board would be violently seasick, throwing up over the railings.
It would be a nightmare.
So large passenger ships are intentionally designed with a much smaller metacentric height, usually sitting at a gentle 0.3 to 0.7 meters.
They are still perfectly safe and will right themselves, but they have a much slower, softer, more gentle, sweeping roll. The torque is lower, which keeps the passengers comfortable and completely unaware of the massive fluid forces battling beneath their feet.
It's a brilliant, highly tuned application of statics. But we don't just deal with fluids resting in massive oceans or static tanks. What happens when we take a tank of fluid and violently put it into motion?
This leads us to a concept called relatively stationary states.
Let's visualize this. Imagine you are sitting in the passenger seat of a sports car and you're holding a completely full, open cup of coffee.
A risky move.
Very risky. The car is stopped at a red light. The surface of the coffee is perfectly flat and level with the earth, but the light turns green, and the driver stomps on the gas pedal, accelerating hard in a straight line.
The coffee violently sloshes backward towards you.
Exactly. And then, as long as the acceleration remains constant, the surface of the coffee stabilizes, but it's no longer flat. It's locked at a tilted angle, rising up the back of the cup.
Yes, the fluid surface adapts to the combination of gravity pulling down and the inertial force pushing back. And the mathematics give us the exact formula for that final resting angle.
What's the math?
It's elegantly simple. Tan theta equals A divided by G.
So the tangent of the angle of the fluid surface equals the car's horizontal acceleration, a, divided by the vertical acceleration of gravity, g.
Exactly. So if you know gravity is a constant, the only variable dictating that angle is the car's acceleration.
That means the tilted fluid surface is literally acting as a physical, highly accurate accelerometer. You could mathematically calculate the exact 0 to 60 speed of that sports car just by looking at a photograph of the angle of your coffee.
It's a beautiful physical relationship, and it gets even more visually striking and mathematically complex if you introduce rotation.
Oh, like spinning.
Right. Instead of driving in a straight line, imagine you take a cylindrical glass vessel filled with liquid, place it on a motorized turntable, and spin it rapidly around its central vertical axis.
Just like stirring a cup of tea really fast.
Exactly. As it spins, centrifugal force pushes the liquid outward against the glass walls. The surface of the liquid dips down deep in the dead center and rises high up on the outer edges. It forms a perfectly smooth, sweeping, concave bowl shape.
Okay.
In mathematics, this is known as a rotating parabolic curve.
And again, the math perfectly predicts reality. There is a precise equation that plots exactly how deep the center will dip and how high the edges will rise.
Yes. The formula is z minus h0 equals omega squared times r squared divided by 2 times g.
Which basically means the curve is based solely on the angular velocity, how fast you are spinning the turntable, and the radius. You can plot the entire parabolic bowl shape on a graph before you ever turn the motor on.
What is truly fascinating to me about both of these examples, the straight line accelerating car and the spinning cylindrical bucket, is how fluid engineers actually handle them mathematically to keep their sanity.
What do they do?
They use a conceptual trick called gyrostatics.
I want to break this down because it sounds incredibly intimidating. Gyrostatics.
It sounds complex, but it's really a shift in perspective. If an engineer tries to calculate the complex, sloshing, swirling and forces of that fluid relative to the solid earth outside the car, the math is a nightmare. It's a dynamic, moving system.
So how do they fix it?
Rather than doing that, the engineer simply shifts their coordinate system. They attach their imaginary X, Y, and Z grid lines directly to the moving car, or the spinning bucket itself.
It's like when you are riding on a smoothly accelerating high-speed train. If you look out the window, the world is flying by at 200 miles an hour. It's chaotic.
Right.
But if you close the blinds and just look at the tray table in front of you, everything inside the train feels completely stationary. You just feel a slight invisible force pressing you back into your seat.
That is the perfect analogy. By shifting their frame of reference to the moving vehicle, the engineers can treat this dynamically accelerating, sloshing fluid as if it were perfectly, peacefully at rest.
So clever.
They just invent a fake gravity force pointing backward to account for the acceleration. It's a mathematical sleight of hand that magically transforms a mind-bending dynamic problem right back into a simple, solvable, static problem.
I love that. Work smarter, not harder. Just change your perspective until the math gets easy. But as brilliant as gyrostatics is, eventually, engineers have to face the music. We can't always pretend the fluid is sitting perfectly still in a cup.
No, we can't.
Up to this point in our deep dive, we've looked at fluids at rest or moving uniformly as a single solid block. But what happens when the fluid truly breaks loose?
When it flows.
When it begins to flow, mix, deform, and tear itself apart? How do we even begin to track a million molecules moving in a million different directions?
That is the transition from statics to dynamics.
Mm.
When you have billions of fluid particles moving independently through a pipe or around an airplane wing, you need a highly organized framework to observe them.
Okay.
Historically, in the study of kinematics, there are two main methods to chart the flow. The first is the Lagrangian method.
It's a Lagrangian method. Let's define this.
The Lagrangian method involves picking a single, specific fluid particle, giving it a theoretical name tag, and following it on its entire convoluted journey through space and time.
You tracked everything about it?
You track its exact position, its kaleidoscopic changes in velocity, and its acceleration at every single second.
Here's my analogy for the Lagrangian method to really ground it. Imagine you want to understand the morning rush hour traffic flow in a massive city like Los Angeles.
Good luck with that.
Right. The Lagrangian method is like secretly placing a GPS tracker on the bumper of one specific car, let's say a red Honda Civic, and obsessively tracking everywhere that single car goes.
Okay.
You get a perfect, highly detailed record of that one car's specific experience. You know exactly how long it sat at every stoplight, every traffic jam it hit, every brief highway sprint it made.
But the flaw in that method is obvious, right?
Exactly.
You know everything about the red Honda Civic, but you know absolutely nothing about the thousands of other cars around it.
Yeah.
You don't know if a traffic jam was caused by an accident or just heavy volume. You lack the big picture.
And that severe limitation is why modern fluid mechanics overwhelmingly prefers the second framework, the Eulerian method.
In the Eulerian method, you don't follow the particles. You let the particles come to you.
How does that work?
Rather than following a specific red Honda Civic, you pick fixed coordinates in space, a specific XYZ location. You simply sit there and watch whatever fluid happens to flow past that exact point over time.
Going back to the Los Angeles traffic analogy, the Eulerian method is standing on a highway overpass above a massive 10-lane freeway with a radar gun and a clicker.
Yes.
You don't care where any specific car came from, and you don't care where it's going after it passes you. You are just standing at that specific coordinate, measuring the average speed and density of every single car that passes your exact location right now.
Which is much more useful data.
By placing engineers with radar guns at multiple overpasses all over the city, you build a macroscopic, real-time map of the entire system's behavior.
It is vastly more useful for engineering. If you are designing a pipe, you don't care about the journey of one water molecule. You care about the pressure and velocity of the water hitting the specific bend in your pipe.
Right.
But even with the Eulerian framework, visually understanding how the fluid actually moves and deforms is tricky. So we use three distinct visual concepts: streamlines, streak lines, and path lines.
Let's break these down so we can see them in our mind's eye. A streamline is essentially a theoretical curve drawn on paper.
Drawn mathematically, yes.
It's drawn so that it is always perfectly tangent to the velocity vector of the fluid particles at that exact instant. Because of this definition, fluid can never cross a streamline. It always flows parallel to it.
How would you visualize that physically?
If you sprinkle fine aluminum powder on the surface of moving water and snap a photo with a slow shutter speed, the tiny smeared blurs of the powder show you the streamlines.
That's a great way to put it. Then there are streak lines. A streak line is a bit more physical.
What's the difference?
It is formed by continuously injecting a dye into water or a stream of smoke into the air at a single fixed point in the flow. As the fluid moves, it carries the dye with it, creating a continuous visible line of all the particles that have historically passed through that specific injection point.
Like the classic images of cars in wind tunnels with the white smoke blowing over the hood, those are streak lines.
Exactly.
And finally, we have a path line, which is essentially the physical, real-world recording of the Lagrangian method we talked about earlier. It's the actual recorded path of one specific particle tracked over time.
Like a balloon.
Yeah, like releasing a single brightly colored weather balloon into a storm and tracing its exact, squiggly, unpredictable line across the sky on a map. Now, there is a crucial distinction here regarding how these lines behave.
Which is?
If a fluid flow is steady, meaning the velocity and pressure at any given point never change over time, like water flowing smoothly out of a hose, then streamlines, streak lines, and path lines are all perfectly identical. They overlap exactly. The weather balloon will perfectly follow the smoke trail.
But if the flow is unsteady, like a violently gusting wind or water from a tap, you are actively turning on and off rapidly. Those three lines completely diverge from one another.
The balloon goes wildly off the smoke trail.
The streamlines shift, and the math required to track it becomes monstrously complex. This intense complexity is why dimensionality is so important in engineering. Real fluid flows in the real world are always fully three-dimensional. They have velocity components moving up and down, left and right, forward and backward.
But dealing with complete 3D calculus for every single junction in a massive municipal water system would take a supercomputer forever.
Nobody has time for that.
So engineers do what engineers do best. They simplify. They assume a flow is two-dimensional if it's very wide and uniform, ignoring the slight friction on the sidewalls.
Right.
Or they simplify it all the way down to one-dimensional flow if they just need to know the bulk average velocity of water moving straight through a simple pipe. They intentionally ignore the microscopic 3D complexity to make the mathematics solvable on a practical deadline.
However, there is a critical point where that mathematical simplification fails spectacularly.
Where ignoring the complexity is no longer an option.
Exactly. If you are standing on that Eulerian overpass watching your highway traffic, you might notice that traffic usually flows in smooth, straight, predictable lines. People stay in their lanes.
Usually, yes.
But occasionally someone slams on their brakes or swerves, and the smooth flow erupts into total unpredictable chaos. Cars are weaving, braking, cutting each other off.
And what's that called in fluids?
In fluid dynamics, this sudden, violent leap from smooth order to chaotic mixing is known as the transition to turbulence.
And this transition brings us to one of the most famous and important experiments in all of engineering history, the work of Osborne Reynolds and the transition to chaos.
It's a classic experiment.
In 1883, Osborne Reynolds set up a brilliant, exquisitely simple apparatus in his laboratory. He had a long, straight glass tube connected to a large tank of still water. He allowed the water to flow slowly down the tube, and right at the entrance, directly in the center of the flow, he continuously injected a single razor-thin thread of brightly colored dye.
At very low speeds, the visual result was beautiful. The thin thread of dye traveled straight down the center of the glass tube, perfectly intact. It looked like a solid colored string suspended in glass.
It never mingled with the surrounding clear water.
Never. The fluid was sliding perfectly in parallel, distinct layers, like our deck of cards from earlier. Reynolds classified this smooth, orderly behavior as laminar flow.
But as Reynolds slowly opened the valve at the end of the pipe, increasing the velocity of the water, he hit a tipping point.
The critical velocity.
Suddenly, instantly, without warning, the perfect straight thread of dye violently shattered. It whipped around, curling, twisting, and mixing furiously until the entire glass tube was clouded with uniform color. The orderly layers were gone.
The fluid was tearing itself apart internally, creating microscopic eddies and whirlpools. He classified this chaotic state as turbulent flow.
What made Reynolds a genius was that he didn't just observe the chaos, he decoded it. He discovered that this violent transition from laminar to turbulent wasn't just determined by the raw speed of the fluid.
It was a highly complex interaction of multiple variables battling against each other.
And he managed to distill this complex battle into a single, elegant, dimensionless number, which engineers worldwide now honorably call the Reynolds number.
Let's talk about the physical meaning behind the Reynolds number, because it's legendary. We won't just list the variables. We need to understand the tug-of-war happening inside the pipe.
Yes, let's break it down.
The Reynolds number is a mathematical fraction. The formula is Re equals rho times V times D divided by mu.
Okay, so on the top of the fraction, you have the inertial forces. You have rho, the density of the fluid, V, its velocity, and D, the physical diameter of the pipe it's flowing through.
Think about what those top factors represent. Density and speed create momentum. A dense fluid moving fast has a lot of momentum.
These are the chaotic tearing forces.
Right. They are the forces trying to push the fluid forward blindly, trying to rip the smooth layers apart into turbulent chaos.
Exactly. But on the bottom of the fraction, acting as the divisor, you have mus, our old friend from the beginning of the episode, dynamic viscosity. Viscosity is the stickiness, the internal friction of the fluid holding the molecules together.
So the Reynolds number is literally just a mathematical ratio of the chaotic, tearing inertial forces to the smooth, sticky, viscous forces.
It's a tug-of-war.
Exactly. If the Reynolds number calculates out to a low value, it means the viscosity is winning. The fluid is thick and sticky enough to suppress the chaos, and the flow remains smooth and laminar.
But if it's high...
If the Reynolds number is very high, it means momentum is winning. The speed and density overpower the stickiness, tearing the fluid into violent, chaotic turbulence.
Reynolds meticulously tested this and found that the critical number, the point where flow inside a pipe almost always remains safely laminar, regardless of how much you shake or agitate the supply tank, is around 2320.
What's incredible about dimensionless numbers like the Reynolds number is that they act like the ultimate cheat codes of the universe.
Cheat codes! I love that.
Because it's a ratio, all the specific units of measurement cancel each other out. You aren't left with feet per second or gallons per minute. You're just left with pure physics.
So it scales perfectly.
Yes. It proves that a tiny half-inch glass tube of water in an 1883 laboratory and a massive 48-inch steel crude oil pipeline running hundreds of miles across the freezing Alaskan tundra are governed by the exact same mathematical destiny.
That's why.
If you plug in their respective densities, speeds, and viscosities, and their calculated Reynolds numbers match, their flows will behave identically.
Which is exactly what allows modern engineering to exist. It allows us to build a tiny scale model of a new fighter jet wing, put it in a small, highly controlled wind tunnel, match the Reynolds number by tweaking the air density or speed,
Right.
and know with absolute mathematical certainty exactly how the massive, full-size jet will handle turbulence when it flies through the real atmosphere. It is the bedrock of aerodynamics.
It's incredible. And I have to take a brief second to talk about Osborne Reynolds, the man, because he wasn't just a stoic mathematician.
No, he was a
The
character.
historical accounts paint a picture of a wildly eccentric, fascinating genius. He was an engineering professor at Owens College in Manchester, and beyond turbulence, he actually discovered the destructive phenomena of cavitation, those microscopic, violently imploding vapor bubbles that eat away at steel ship propellers.
But despite his genius, his teaching style was famously, hilariously chaotic.
Yes, the historical accounts of his lectures are amazing. He would apparently often turn his back entirely on his students, standing at the chalkboard mumbling to himself as he attempted to derive massive, incredibly complex thermodynamic equations completely from scratch, just from his own memory.
He would write out this huge, sprawling derivation covering the entire board, step back, stare at it, suddenly shout, "No, that's wrong," and aggressively rub the whole thing out.
Which I'm sure was great for the students taking notes.
Oh, I'm sure they loved it. He'd start over on a completely new track, do it all again, and ultimately conclude out loud that his predecessor, the famous Professor Rankine, was right all along.
That's so funny.
He famously refused to blindly trust any scholar's view, even massive historical authorities, without proving it himself from absolute first principles. That intense, almost stubborn skepticism is exactly what led him to see the hidden mathematical patterns in turbulence that everyone else had completely missed.
It's a great reminder that true science is an active, messy, deeply human process, not just a clean list of facts to memorize out of a book.
Completely agree.
And speaking of messy processes, understanding turbulence introduces us to our final major topic, the macrostructures of chaos, vortices, swirls, and circulation.
Turbulence itself is characterized by pure, unadulterated, microscopic chaos. But sometimes flowing fluids organize that energy. They create vast, highly organized, swirling structures that have enough concentrated power to rip roofs off houses and level entire cities.
Yeah, we have to look at how fluid deforms. As fluid particles flow along, they don't just move forward in a straight line, they deform, they stretch out, and they spin.
This introduces the concept of vorticity.
And fluid mechanics breaks massive rotational flows into two distinct categories that honestly sound totally backwards and contradictory when you first hear them: the forced vortex and the free vortex.
Let's define them very carefully, because the distinction is beautiful. A forced vortex is what engineers call a rotational flow.
This goes back to the spinning cylindrical bucket of water we talked about earlier.
Yeah.
You put a bucket of water on a motorized turntable and you physically force it to spin.
Right.
The fluid rotates around the center of the bucket, and the velocity of the water actually increases as you move outward toward the edge, just like the outer edge of a vinyl record moves faster than the inside track.
But here is the key defining feature of the forced rotational vortex. Each individual microscopic fluid particle is actually spinning on its own central axis.
How do we visualize that?
If you want to visualize this, imagine dropping a tiny rectangular wood chip into that spinning bucket. The wood chip will travel in a large, sweeping circle around the bucket, but the chip itself will also rotate 360 degrees as it travels.
Okay, so it's rotating macroscopically around the bucket and rotating microscopically on its own axis.
Exactly. In contrast, a free vortex is categorized mathematically as an irrotational flow.
Which sounds wrong.
It really does. This is the classic everyday example of water draining out of a bathtub or a whirlpool forming in a river. The fluid is swirling rapidly in a circle around a central point. But unlike the spinning bucket, the velocity profile is reversed. The water is actually moving the fastest right near the center hole, and the speed drops off inversely proportional to the radius as you move outward.
Okay, wait, stop right there. I have to push back on this terminology because this is where the math feels like a prank. You are calling a free vortex where water is literally swirling around a bathtub drain in a massive circle.
Yeah.
You are calling that irrotational.
Yeah, that's what it's called.
That makes absolutely no sense to me. I'm literally standing over the bathtub watching the water rotate in a giant circle right in front of my eyes. How is that irrotational?
It is the most common point of confusion in fluid kinematics. The key to unlocking it is separating the macroscopic path of the bulk fluid from the microscopic state of the individual fluid molecules.
Okay, explain.
Yes, the water as a whole mass is traveling in a large circular path around the drain. But the microscopic fluid elements do not rotate on their own internal axis.
Okay, so let's use the wood chip test again. If I drop my tiny rectangular wood chip into the bathtub drain vortex, what happens?
If you drop the wood chip in, it will absolutely travel in a large circle around the drain, but the chip itself will always point in the exact same compass direction.
Oh, wow.
If the painted tip of the wood chip is pointing perfectly north when you drop it in, the tip will continue pointing perfectly north for the entire 360-degree circular journey around the drain. It never spins on its own axis. It just translates in a circle.
That complete lack of microscopic internal spin is what makes the flow mathematically strictly irrotational.
That is a brilliant distinction. The macroscopic circular path versus the microscopic internal spin. That completely solves the paradox.
And what's truly terrifying is when nature decides to combine the two.
Like when?
Natural phenomena, like massive hurricanes and tornadoes, are incredibly complex combinations of both vortex types. They feature a deadly high-speed forced rotational vortex right at their very core, the eye wall surrounded by a massive, sprawling, free irrotational vortex on their outer periphery.
And engineers have to find a way to quantify these massive swirling motions, not just to understand weather, but to build the machines that power our world.
They use the mathematical concepts of circulation and Stokes' theorem.
Stokes' theorem sounds incredibly intimidating. It involves clothesline integrals, but physically, it's just a way of adding up the rotation.
Yes. The math states that gamma equals the clothesline integral of Vs with respect to ds. Or in other words, if you take the surface integral of the vorticity over an area, it is exactly equal to the total circulation around the closed curve boundary of that area.
So practically speaking, if I want to find the total circulation, I just trace a closed loop, a big circle inside the moving fluid, and I mathematically add up every single velocity vector that is pointing along my path. It gives me a master number for the swirling power of that area.
Exactly. And this isn't just abstract chalkboard math. Stokes' theorem is the foundational mathematical blueprint used to design incredibly complex machinery.
Like what?
It is how engineers shape the beautifully curved metal impellers inside the water pumps, keeping your car engine cool, or the massive spiraling centrifugal blowers pushing air through skyscraper HVAC systems.
Oh, so they use the circulation math to design the blades.
Exactly. By calculating the exact mathematical circulation of the fluid, they can sculpt the metal blades to slice into the water, capture that rotational energy, and move the maximum amount of fluid while burning the absolute minimum amount of electrical energy.
It's just astonishing how these invisible mathematical rules dictate absolutely everything around us. It's like seeing the matrix.
It really is.
We've gone from understanding the microscopic elastic surface tension of a morning dewdrop to realizing the slight 0.005% compressibility of water is the only thing allowing whale songs to travel across the oceans.
We've covered a lot of ground.
We really have. We've visualized the chaotic Reynolds transition shattering a smooth flow of dye in a glass pipe, and we've decoded the swirling dual vortex mathematics powering a Category 5 hurricane.
And that is the true grand takeaway here. These concepts, viscosity, buoyancy, the Reynolds number, Stokes' theorem, they aren't just arcane equations scrawled on a chalkboard by an eccentric, mumbling professor.
No, they're everywhere.
They are the fundamental governing rules of physical reality. The exact same principles of fluid mechanics that dictate the crushing torque on a massive concrete hydroelectric dam also dictate the exact pressure of the blood pumping through the veins in your neck right now.
It's incredible.
They govern the chaotic weather fronts forming outside your window, and they dictate the aerodynamic drag on the car sitting in your driveway.
It connects absolutely everything. You can't unsee it once you learn it. And as we wrap up, I want to leave you, the listener, with a final, highly provocative thought. Something to chew on that builds entirely on what we've learned today.
What is it?
Think back to Osborne Reynolds. Think about that Reynolds number and that violent, chaotic transition from smooth, easy laminar flow to turbulent chaos. Turbulence creates massive parasitic amounts of aerodynamic drag and friction.
It is the ultimate enemy of mechanical efficiency.
Exactly. Now, what if modern aeronautical engineers could find a way to actively, perfectly control that boundary layer of air flowing over a commercial airplane wing in real time?
That would be amazing.
Right. What if, using millions of microscopic sensors and tiny active physical adjustments on the wing surface, they could artificially suppress the Reynolds transition?
Delay the turbulence.
Exactly. If they could delay turbulence at will, forcing the air to remain in that smooth, frictionless, laminar state across the entire width of the wing, regardless of how fast the plane is flying, the energy savings would be astronomical.
It would completely revolutionize global travel.
It really would. It would slash aviation fuel consumption by incredible margins and fundamentally alter our carbon impact on the planet's atmosphere. It is considered the holy grail of fluid dynamics, and achieving it relies on mastering the very equations we just spent the last hour discussing.
Just something to ponder the next time you're sitting in a window seat at 30,000 feet, looking out of the wing, watching the invisible, chaotic air rush by.
It perfectly reminds us that there is always more to learn. The universe is incredibly complex, and the rigorous application of this knowledge can literally change the world.
That's exactly why we do this. We started by looking at a tiny dewdrop and a massive hurricane and realized they are speaking the exact same mathematical language.
If you haven't already, give us a like and follow, and please leave us a comment if you enjoy the podcast. We love to hear from the folks who make this possible.